Dear physics aspirants, right now I have the physics book of +2 level, and work, energy and power is the topic, and under this topic the subtopic 6.8 of NCERT book, the conservation of mechanical energy, will be discussed by me. For this I am giving you the figure 6.5 for your understanding, the conversion of potential energy of kinetic energy for a ball of mass dropped from a height h. You can see here the diagrammatic understanding is very important for the understanding of the subject matter. Here you will see the conservation of mechanical energy. For simplicity, we demonstrate this important principle for all dimensional motion. Suppose that body undergoes displacement, acts under the action of a conservative force F. Then from the WE theorem we have as K is equal to Fx into x, that is the displacement. If the force is conservative, the potential energy functions Vx can be defined such that minus V and is equal to Fx and x. The above equations imply that K plus V is equal to 0 and K plus V is equal to 0. 6.10. Here you will see, which means that K plus V, the sum of the kinetic and potential energies of the body, is a constant over the whole path I and to xf. This means that Ki plus V whole xi is equal to Kf is plus Vxf. 6.11. The quantity K plus Vx is called the total mechanical energy of the system. Individually, the kinetic energy K and the potential energy Vx may vary from point to point, but the sum is constant. The aptness of the term conservative force is now clear. Let us consider some of the definitions of the conservative force. A force Fx is conservative if it can be derived from a scalar quantity Vx by the relation given by equation 6.9. The three-dimensional generalization requires the use of vector derivative, which is outside the scope of this book. 6.9 equation is here. You will see the work done by the conservative force depends only on the end points. This can be seen from the relation W is equal to Kf minus Ki is equal to Vxi minus Vxf, which depends on the end points. A third definition states that the work done by this force is a closed path is 0. This is once again apparent from equation 611, since xi is equal to xf. 611 is here equation. Thus, the principle of conservation of total mechanical energy can be stated as the total mechanical energy of a system is conserved if the forces doing work on it are conservative. The above discussion can be made more concrete by considering the example of the gravitational force once again, and that of the spring force in the next sections. Figure 6.5 depicts a ball of mass m being dropped from a cliff of height h. 6.5 conservation of potential energy of kinetic energy for a ball of mass m dropped from a height h. The total mechanical energies E0, EH and EH of the ball at the indicated heights 0 ground level h and h are EH is equal to mgh 611a, EH is equal to mgh plus half mb square h 6.11b, E0 is a half mb square f 611c. The constant force is special case of separately depends force Fx, hence the mechanical energy is conserved. Thus EH is equal to E0 or mgh is equal to half mb square f and Vf is equal to 2gh root, a result that was obtained in section 3.7 for a freely falling body. Further, EHE is equal to EH. A result that was obtained in section 3.7 for a freely falling body. Further, EH is equal to EH, which implies V square H is equal to 2G H minus H 6.11D, and is some familiar result from kinematics. At the height H, the energy is purely potential. It is partially conserved to kinetic at height H, and is fully kinetic at ground level. This illustrates the conservation of mechanical energy. And here is the example: a bob of mass m is suspended by a light string of length L, you will see here. And with the help of this picture you can understand, and here is the solution. With the help of this solution you can understand the subject matter. I am trying to give the information regarding this, and the answer is here, and here in the left answer is here. So at point C, the string becomes slack and the velocity of the bob is horizontal, and to the left it is connecting string is cut. At this instant, the bob will execute projectile motion with horizontal projection akin to a rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue on its circular path and complete the revolution. So in next video I will share a lot more regarding the potential energy of a spring. Thank you for watching the video. Thank you very much.